So first of all, I'd like to thank the organizers for granting me the opportunity to give a talk here. And also, I'd like to express my gratitude to my supervisor, John, for supporting me. So recently, Hill and Verity have developed the theory of infinite cosmos. So roughly speaking, infinite cosmos are quasi-categorically enriched categories resembling fibrous objects. And the theory provides a setting for understanding infinity-1 categories with structure and their pseudomorphisms. So take a look at the following examples. We have quasi-categories that admit limits of shape J for a simplicial set J, and a map that preserve the limit, and also Cartesian vibrations between quasi-categories and the Cartesian functors. So, Hill and Verity have shown that any infinite cosmos admits all flexible weighted limits. So, flexible weighted limits are analogous to pi limits in two-category theory. Examples include products, inserters, and common objects. So, the idea behind is that the diagram commutes up to a higher morphism instead of commuting strictly. So we've just seen that's the case for infinity-1 categories with structure and the pseudomorphisms have been studied. Then what about infinity-1 categories with structure and the lax morphisms between them? So what kind of limits do they exhibit? So let's take a look at this theorem by Hill and Verity. Let A be a quasi-category admitting limits of shape J for a simplified set J. Let T be a monad on A, which is not limit-preserving. Then the quasi-category of algebras, or say the Eilenberg-Moore object, T out over T, also admits limits of shape J, and the projection preserves the limits. So in other words, the forgetful functor from T out to A lifts the limits of shape J. So we would like to know if this also holds for models other than quasi-categories and limits other than Eilenberg-Moore objects. So in other words, our goal is to investigate what kind of limits exist in infinity-1 categories with structure and the lax morphisms between them. So the approach we will be using is inspired by Lack and Schumann. Lack has studied two-dimensional limits involving lax morphisms, and he has shown the following. Let A, B, C be categories admitting limits of shape J for a category J. Let F and G be functors where G preserves limits. The common object of F and G also admits limits of shape J, and the projections preserve and reflect them. So from this, we see that the answer to limits involving lax morphisms requires a mixture of pseudo and lax morphisms. So taking inspirations from Lack and Schumann, we not yet, sorry. So this phenomenon has led Lack and Schumann to develop enhanced two-category theory. So roughly speaking, an enhanced two-category is a two-category with two types of morphisms, tight and loose, and where the tight ones are also loose. So let's take a look at this example, Kaplan. So we have categories admitting limits of shape J for a category J, and we take the tight morphisms to be the functors that preserve limits, and the loose morphisms to be just the functors, not necessarily preserving limits. So taking inspirations from Lack and Schumann, we introduce the notion of enhanced simplicial categories. So roughly speaking, they are simplicial categories with two types of zero arrows, the tight ones and the loose ones. And we can formulate them via enriched category theory. So let's go to the formulations. Denoted by set delta square, the arrow 1 category of the category of simplicial sets. So this means that it has objects given by the simplicial maps, and for a morphism from a simplicial map F1 to another simplicial map F2, it consists of a pair Fs, Ft, such that this square commutes. And then we denote by F delta the full subcategory of that R1 category spanned by the fully faithful and injective on vertices simplicial maps. And note that this F delta is complete and co-complete and also Cartesian closed. So now we arrive at our definition. An enhanced simplicial category is a category enriched in F delta. So unraveling, this means that for an enhanced simplicial category A and two objects AB in A, the mapping space AAB is a fully faithful and injective on vertices simplicial map. So this means that we have two types of zero arrows, where the tight ones can be fully embedded into the loose ones. So take a look at this example of J-lim. So we have infinity 1 categories admitting J-shaped limits for a simplicial set J. And we can take the tight zero arrows to be the infinity 1 functors that preserve limits. And we take the loose zero arrows to be just the infinity 1 functors. And J-lim admits several kinds of limits. So for instance, products. So if A and B are in J-lim, then so is their product A times B, and both the projections from A times B to A and A times B to B preserve limits, and they jointly reflect limits. Second, J-lim admits also simplicial powers. So if A is in J-lim and X is a simplicial set, then A to the power of X is also in J-lim. And projections also share the nice properties. And third, J-lim admits limits of countable chains of tight isovibrations alongly. So let's take a look at this countable chains of tight isovibrations in J-lim, which means that each of these arrows are limits preserving and they are isovibrations. Then the projective limits of this chain also exist in J-lim, and the projections preserve and jointly reflect limits. So now we introduce a kind of limits called rigged N-inserters. So rigged N-inserters are higher dimensional inserters that insert a higher cell among arrows of a lower dimension. So in other words, they generalize the usual inserters. And also, they serve as higher dimensional analogs of equifiers. So let's take a look at the definition first, and I will explain. So let K be an enhanced simplicial category, and S and T be infinity categories in K. Suppose that K admits simplicial powers. Let D be a zero arrow from S to T to the power of the boundary of delta n, the standard simplest, where the composite of D with the evaluation map at the terminal vertex n is a tight zero arrow. Then the terminally rigged N-inserter of D is defined to be the pullback of D along the restriction. In practice, we would require the projection P to detect tightness. So by detect tightness, I mean like the reflection of limits. So let's demonstrate how rigged N-inserters recover the usual notion of inserters with tight codomains. So consider when n equals 1, then D is a zero arrow from S to T times T. So it consists of a pair F from S to T and G from S to T, where G is tight. So recall that the composite of D with the evaluation map at the terminal vertex has to be tight, and therefore we have to pick, say, G to be tight. Then the Briggs inserter is given by the pullback of Fg along the domain and codomain projections. So in diagram, it looks like this. The domain of phi is given by Fp and the codomain of phi is given by Gp, and this is exactly the usual inserter with a tight codomain. And next, Briggs and inserters also recover common objects with tight codomains. So again, n equals 1. And this time, suppose that our enhanced simplical category admits also powers, which is the case in JLIM. So put S equals A times B. Then D is a zero arrow from A times B to T times T, and it consists of F from A to T and G from B to T, where G is tight. And again, the Briggs inserter is given by the pullback of Fg along the domain and codomain projections. And the diagram, it looks like this. So it is exactly the usual common object with tight codomain. And finally, let's see how Briggs and inserters give us a sense of equifiers. So this time, let n equals 2. And then D is a zero arrow from S to T to the power of the boundary of delta 2. So in other words, D is a triangle in the mapping space home ST. So let's first fix A to be a zero arrow from S to T, and B to be a zero arrow from S to T, and F and G to be one arrows from A to B. Then we let D be presented by this diagram. So one of the edge of D is given by F, and one of the edge is given by G, and the remaining edge is given by this degeneracy. Then again, the Briggs inserter is given by the pullback of Fg degeneracy along the restriction, and in diagram it looks like this. And if we are in a 2 category, then this triangle would collapse, and therefore giving us the usual diagram for an equifier, which says Fp equals Gp. So, and there is, we have established the result that JLIM admits Briggs and inserters, and the projection preserves and reflects J-shaped limits. And therefore, JLIM admits inserters with tight codomains, and hence common objects, and also common objects with tight codomains. And what about analogous objects? So indeed, analogous objects over loose monads can be built from basic limits, which are simplical powers, Briggs and inserters, and limits of countable chains of tight isovibrations. So the construction is as follows. So given a monad T from A to on A in, say, cat-limb, taking inserter would equip A with the structure morphisms. So consider the inserter of T and the identity on A. Then an object of L consists of a pair, small a, which is an object in big A, and a structure morphism, alpha, from TA to A. And then taking equifiers would give us associativity and the unitality. So if we take the equifier of phi t phi and phi mu p, evaluating at A alpha gives us this square, this commutative square, which is exactly associativity for an algebra. And if we take the equifier of phi eta p and the identity, then evaluating at A alpha gives us this commutative triangle, which is exactly the unitality. So in other words, the analogous objects can be built step by step as follows. So first of all, we take the inserters to equip A with the structure morphisms, and then we take an equifier to impose the associativity, And next, we take another equivalent to impose the unitality. And if we are in an infinity categorical world, this process will go on and on because we are not going to ask for equality anymore, but isomorphisms. And therefore, we will be taking a countable chains of rigged and inserted. And that's why from simplicial powers and rigged and inserters and limits of countable chains of tight isovibrations, we will get Eilenberg-Moore objects. And we have this result. So J-lim admits Eilenberg-Moore objects over loose small knots and therefore gets referred to preserve and reflect J-shaped limits. So note that this result applies to any model of infinity one categories. So it generalizes the results by Hu and Verity on quasi-categories. And also we have included the enhanced aspect of the projections, which means that we have included the reflection of the limits by the projections. So now, what about infinity one categories with J-shaped co-limit? Or other exotic things like Cartesian vibrations between infinity one categories and the functors between them? So to understand those exotic things, we need to introduce the enhanced simplicial category, lolly K. So let's K be an infinity cosmos. Denoted by lolly K, the enhanced simplicial category with objects given by the isovibrations in K, which are lollies, left adjoint, left inverses. And the tight zero arrows given by the morphisms of lollies, and the loose zero arrows given by just the morphisms of isovibrations. And for the higher arrows, we just take the usual higher arrows for isovibrations. Hu and Verity have shown that zero exotic infinity cosmo can be extracted from the infinity cosmo of lolly K or dually rally K. So here, lolly K, we mean the infinity cosmo of isovibrations, which are lollies, and the morphisms of lollies. So we're taking the pseudo-morphisms. So these include infinity one categories with J-shaped limits or co-limits, and there are pseudomorphisms, which means that limits preserving or the co-limits preserving infinity one functors, and Cartesian vibrations or co-Cartesian vibrations between infinity one categories, and discrete Cartesian vibrations or discrete co-Cartesian vibrations. So this means that lolly K or dually rally K serves as the core of many interesting exotic things. So this means that it will be very nice if we can obtain our result in, say, lolly K, because that would mean that we will obtain the same result for all these exotic things. And a good news is that we have established the following theorem. So the enhanced simplicial category, lolly K of lollic isovibrations in an infinity cosmos K admits terminally rigged and inserted, and the projection is exact and detects exactness. So by lollic isovibrations, I mean isovibrations that are lollies. And by exact, I mean being a morphism of lollies. So tight. And similarly, we can show that lolly K admits simplicial powers and also limits of chains of tight isovibrations. So together with this theorem, we deduce that the enhanced simplicial category of lollic isovibrations in an infinity cosmo K admits Eilenberg-Moore objects over loose monods, and the forgetful functor is exact and detects exactness. And so from the results in lolly K, we will obtain that the enhanced simplicial categories of Cartesian vibrations between infinite one categories and that of discrete Cartesian vibrations both admit rigged and inserters, and therefore also Eilenberg-Moore objects over loose monods, and the forgetful functor is tight and detects tightness. And for the dual case rally K, we should adjust our notion of rigged and inserter. So recall that categories with J-shaped co-limits admits co-animate objects over loose comonads. So if we are looking for co-algebras, then the structure morphisms would go from A to TA instead of TA to A. And therefore, when we take the inserter, we will be looking for a tight domain instead of a tight codomain. And therefore, we should consider initially rigged and inserted instead of terminally rigged. And we're now working on this result. So a dual version of the previous theorem. That's the enhanced simplicial category, Rayleigh K of Rayleigh isovibrations in a cosmos admits initially rigged and inserted, and the projection is exact and detects exactness. And from this, we will deduce that the enhanced simplicial category of infinity 1 category with J-shaped co-limits and the co-Cartesian vibrations between infinity 1 categories and also the discrete co-Cartesian vibrations all admit initially rigged and inserted and consequently co-animate objects over loose comonads. And that's all for my talk. Thank you for your time. Very
much, Joanna. Questions? Please, Richard.
Thank you for the talk. That's very interesting.
Thank you.
So I'm just interested in the proof of the fact that from the rigged and inserted, you can construct kind of more objects.
Yeah.
So in Real and Verity's paper, they show that the simplicial category that classifies monads can be described via a simplicial computat. So do you use that and then somehow say that if I've got any weight that's presented by a simplicial computat, then I can compute it from these rigged inserted?
No, I haven't used anything about computat. No.
Okay.
So, oh, sorry. So it's just I just proved directly that that pullback, the definition of a rigged and inserted exists in Rayleigh K. Yeah, with by constructing some lift to solve a lifting problem. Yeah.
Okay, John.
Yeah, the width for Eilenberg-Mur objects, right? So real and verity show it's sort of the co-limit of a chain of things, and so you can use that to compare it with the rigged and inserters.
Thank you.
Yes, you go first. Adrian has one side. Go back to Adrian, but you go here.
If instead of simplicial sets, you consider more general Rayleigh category in which you can talk of embeddings, do you think you can get the notion of general enhanced enriched category?
I haven't yet thought of it. So yeah. Now I'm just focusing on enhanced simplicial categories because I was
I like your idea. It's simple. Take embeddings in simplicial sets and enrich over the F delta that you get. But why not go more general?
Oh, okay. Thank you.
Maybe.
So, interestingly, my question was, I guess, a special
Thanks.
You're too gentle. But I was thinking of the, so in low-dimensional settings, we apply this theory to ordinary Q category theory, you get an interesting new perspective. So I was wondering whether you could also take V equals gray, so that specific base, and also get new interesting results.
I also haven't thought about it, but thank you. Maybe, yeah.
Suggestions? Other questions? Any others at all? It's Friday afternoon. It's 5 to 6. I think we're all going to thank Joanna again.